Hello students, welcome to lecture 7 of the online course on Introduction to Microwave and Optical Metamaterials. In this lecture, we will continue the basic electromagnetic theory. So, here is the lecture outline. We will discuss about the 4 Maxwell's equations in more details. The first one we will take up as the Gauss law for electric fields. The second one is all of you know, Gauss law for magnetic fields, Faraday's law, and then we will look into Ampere's equation and then what Maxwell contributed to that, and that has finally become the 4th equation in that set of Maxwell's equation, which is also known as Ampere-Maxwell's equation. From that we will see how we can obtain the wave equation from the Maxwell's equations and also how we can obtain speed of electromagnetic waves. So, students, let us discuss about Gauss law for electric field first. Okay. So, just a background about that, this law was published posthumously in 1867 as part of collection of work by the famous German mathematician Gauss. Okay. So, if you look into the Maxwell's equation, it is basically set of 2 divergence equation and 2 curl equations. So, let us focus on the first one here, okay, and this particular law is called the Gauss law for electric fields. Now, how you understand or interpret this law? It says del dot D equals rho f. Okay. So, let us assume that you have a closed surface called S and the total charge that is inside this closed surface is basically Q. So, you can say that the charge Q is basically enclosed by this closed surface S. So, n cap shows the normal from the surface, okay, and these are the 3 coordinate vectors Ex, Ey and Ez. Now, this Gauss law also tells that the flux of the electric field that is passing through this closed surface S is basically equal to the total charge that is enclosed in this surface divided by the permittivity. So, if you assume that the material within the surface is vacuum or air, so the permittivity is only epsilon naught. So, the right side basically becomes the total charge, that is Q divided by epsilon naught. And how do you calculate the total flux of the electric field through this surface? So, you take electric field vector and you calculate what is coming out normally. So, you take a dot product with this surface normal n cap and then you integrate it over the entire surface. So, this gives you the total flux that comes out from this closed surface S, and that is equal to the charge Q enclosed by this surface divided by the vacuum permittivity. Right. So, one of the great features of this particular law is that S can be any surface. You do not need to think of a sphere or a cube or any other regular shape. It can be any surface that can completely enclose the charge distribution, okay, and then the flux through this surface can be calculated in the similar way, and then you can find out the total amount of charge that is enclosed divided by epsilon naught. Now, moving ahead, when you take that equation, the calculation of the flux, okay, in this form, you can also take help of the divergence theorem, and that will help you to obtain the differential form that you are seeing here. So, this particular equation is in basically differential form, and this is the one shown in the integral form of the Maxwell equation, and how you can go back and forth from one form to the other form. So, you can see here that this particular one can also be written as the divergence of E over this surface, okay, over this volume. Okay. So, you can have the volume integral of the divergence of E, that is same as the surface integral of the electric flux, and Q by epsilon naught can be simply written as Q is nothing but the total amount of charge. So, if you know the surface charge volume charge density rho, okay, if you know the volume charge density rho and you integrate it over the volume, so integration rho dV is basically giving you the total amount of charge enclosed. So Q by epsilon naught can be replaced by this. So what we are doing in this equation, the left hand side can now be written as this. So it's basically a volume integral of the divergence of the electric field, and the right side, which was basically Q by epsilon naught, can now be written as volume integral of the charge density over epsilon naught. So you can just put this left side and right side, and you see both are basically taking the volume integral. So what is happening, the quantities within the integral are basically now the same. That's how their integration is also yielding the same result. So you can say del dot E equals rho by epsilon naught. Okay. Now if you multiply this E vector with epsilon naught, what you get is d, the electric flux, and this is particularly this equation. So now let's move on to the second equation, which is basically Gauss law for magnetic field. So this particular equation we are talking about. Del dot B equals 0. What is B? B is basically the magnetic flux. Okay. Now the Gauss law for magnetism basically states that no magnetic monopole exists and that the total flux through a closed surface must be 0. Okay. This is also true that because the total flux through a closed surface becomes always 0, that means you cannot separate out the poles and only keep a positive pole or a north pole, and you do not have a south pole along with it. Okay, that is not possible. Okay. So you can say that the number of magnetic field lines that enter and exit through an arbitrarily closed surface S will always remain the same. So this particular thing, so here you can see a bar magnet. So this is how the magnetic field lines are exiting from the north pole and it is entering the south pole. But now if you think that you can simply split this magnet into two and make only north pole and only south pole, that's not going to happen. When you break them into two smaller magnets, they themselves also have north pole and south pole, and the field lines will behave exactly in the same way as the earlier larger magnets. So how do you derive this del dot B equals 0? It is basically coming from this particular integral form. So you can integrate the magnetic flux over the surface, closed surface, and that will come out to be 0. And that is because, so if you think of any surface like this, so from the positive pole the lines are basically exiting, but because of because north pole it is exiting, for the south pole that many lines are only entering. So if you think of enclosing this particular magnet in a closed surface, you will see that the number of magnetic field lines exiting that surface because from the north pole end will be equal to the number of field lines entering into the surface again because of the south pole. So the net flux will be 0. So now let us look into the third one, which is called the Faraday's law. Okay. So this is one of the first two equations that basically connect the electric and the magnetic field. Okay. So you can see that here E is basically now dependent on or connected with B as well. So it is telling you that E is a conservative field in the absence of a magnetic field, or if the magnetic field is basically constant in time. It means if magnetic field is not there at all or the magnetic field is constant, then this term becomes 0. In that case, the electric field is a conservative field. Now this electromagnetic induction was basically discovered independently by two scientists, Michael Faraday in 1831 and Joseph Henry in 1832. So Faraday was the first to publish the results of his experiments, so this particular equation got its name. So we will call this as Faraday's law, and the Faraday's law of induction in the integral form looks like this. Okay. So these are all in the differential form, as you can see. In the integral form, this is how it looks like, and it tells you the story in a much comprehensive manner. So, here you can see the line integral of the electric field around a closed loop. So, this tells you about a closed loop line integral. Okay, that is how the symbols are shown. Okay. So, the line integral of the electric field around a closed loop is basically equal to the negative of the rate of change of the magnetic flux. This is the magnetic flux enclosed by the loop. Clear? So, there are a couple of things here, as you can see, d dt tells you the rate of change with time. This particular integration is giving you the net magnetic flux through any surface which is bounded by this closed path C. Okay. And what are this, you can see here dl is basically telling you a infinitesimal small length of this closed path, and you are basically doing a dot product. So, E is also a vector, dl is a vector. So, the component there is a dot product. So, you are basically computing the modulus of E, modulus of dl, and then cos theta, right. So, this is basically the induced electric field vector because of the change in the magnetic flux, right, and this is how you obtain it. Fine. So, the direction of this electromotive force, okay, is given by Lenz's law, and you all know that Faraday's law is the basis for electric generators, and it also forms the basis for inductors and transformers. So, it is a very important law in electromagnetism. So, you can also see this is how it is written in the differential form, and you can always go from the integral form to the differential form by using some of these theorem that you have already studied. So, I will quickly tell you what it shows here. So, from curl of E equals minus dou B dot E, that also tells you about the physical meaning behind this is that a changing magnetic field will basically produce a circulating electric field. Okay. So, here also you can see that when the magnetic field lines are, or you can see the magnetic field line is kind of at the center of the loop. Okay. So, the current induced is 0, but as it moves away or it goes in, you get a negative current. When it comes out, you get a positive current or vice versa, okay, depending on the magnetic poles, whether the north pole is this side or the other way. So, this basically tells you how the current is introduced because of the time varying magnetic field, and that is basically recorded in the galvanometer. Now, if we go back to this particular form and we try to use Stokes theorem. So, on the left hand side we have seen that we have a closed loop line integral. Okay. So, E dot dl over a closed loop, and you can use Stokes theorem. So, you can convert this line integral into a surface integral of the curl of that vector. Okay. Now, this is same as, so on the right side also you already have a, you can see from here you already have a surface integral. So, it is easy to write down these two equations side by side, and you see you are calculating both the surface integrals. So, what is happening, whatever is getting integrated, that quantity is now basically matching on both sides. So, you can see that curl of E is basically minus d dt of bt. So, that is how you can get this differential form equation. So, this is very simple. E represents the induced electric field vector. This is basically del cross, that means you are basically taking the curl. So, you are getting a circulating electric field which is basically coming from a time varying magnetic flux, or you can say the rate of change of the magnetic flux density vector gives you the circulating electric field, which is also seen here. When the magnet is basically moving, the flux that is going through these lines are changing. So, that induces different amount of current, and the direction of the current also reverses based on whether when the magnet is going in and it is coming out, because the field lines come out, the magnetic field lines come out from the north pole and it goes into the south pole. Now, we move on to the last law in the Maxwell's equation. So, before Maxwell actually put them together, all these laws were known independently. Okay. So, world actually knew the first half of this particular equation, okay, and it was known as Ampere's law, and it is very simple that it says that if you have a wire or a conductor carrying current, then this current will produce a magnetic field that will basically circle the wire. Okay. So, Ampere basically had shown how to make magnetism from electricity. So, a current carrying wire can give you a circulating magnetic field. Now, what are the direction? How you can do it? You can actually get the field direction, magnetic field direction from the right hand thumb rule. So, if you put your thumb pointing in the direction of the current, okay, your fingers will curl, your fingers of your right hand will curl, indicating the direction of the magnetic field. Okay. So, that is how it is following the right hand thumb rule. So, you can also write Ampere's law in the integral form. So, we will see how where it comes from. It basically starts with the magnetic field, okay, that is there in the because of this current carrying wire. What is the magnetic field that you can obtain from the Biot-Savart law? So, you can write that the magnetic field due to a long straight wire will be simply B equals mu naught I by 2 pi r. So, what are these? These are basically mu naught is the vacuum permeability, I is the amount of current, and 2 pi r is basically the circumference, okay, of the wire. Okay. Now, since you know that B and dl in this particular case, so dl is basically the circulating current loop, the distance along which the magnetic field lines are circulating. So, you can take B and dl in the same direction. So, you can write B dot dl equals B dl cos 0. Ideally is theta, but then they both are in the same direction. So, you can take theta equals 0. So, that gives you B dl. So, now if you basically integrate it along this closed loop, so you write closed integral, line integral of B dot dl, and that will be equal to so B you already know, that is basically mu naught I by 2 pi r. So, what you are left with? You are basically left with this integral of dl, right. So, when you take the integration along the closed loop, you will get nothing but 2 pi r. Okay. So, this closed line integral will basically give you 2 pi r. So, this 2 pi r and 2 pi r cancels out. So, what you get is simply line integral of B dot dl equals mu naught I. Okay. So, this is the integral form of the Ampere's law for the static fields. Okay. Now, you can also write down the Ampere's law in the differential form. So, what you can do, you can first put B equals mu naught H in the integral form of the Ampere's law, which is this one. We have just seen that the loop or line integral of B dot dl equals mu naught I. So, B can be now written as mu naught H. So, what happens? Mu naught will cancel out from both sides. You will simply have line integral of H dot dl is basically equal to the current enclosed, okay, by that loop, or whatever is the current passing through that loop, right. So, once you have this equation, you can obtain the differential form of the Ampere's law by applying Stokes theorem. So, in Stokes theorem, you can replace this line integral by the curl of the magnetic field, and then it will become a surface integral, right. So, this one you can simply write as curl of H ds. So, that is now the surface integral, and if you know the surface current density, that is J, and if you integrate it over the entire surface, you will get the total current enclosed. So, this term on the right can now be written as like this. So, you can write it as surface integral J dot ds, So, what you are doing again? So, you are bringing everything in the same kind of surface integral. So, whatever is getting integrated will be basically the same thing. So, here you see you are basically equating these two. So, essentially curl of H is nothing but J, because on both sides you are taking surface integral. So, this is what is Ampere's law looks like in the differential form, curl of H equals J. Now, this is incomplete and it is not valid for electrodynamics. Why? Because when Maxwell basically wrote down this Ampere's law, he found that it is not complete, because when he started with the Ampere's law, okay, and then he took the divergence of this Ampere's law on both sides. You see, you take the divergence. So, divergence of a curl is 0. That means divergence of J, which is this one, is becoming 0. But is it always the case? The answer is no. In electromagnetic theory, the continuity equation is an empirical law which expresses local charge conservation, and charge conservation is much more fundamental than Maxwell's equation, and it basically states that the divergence of the current density J in amperes per square meter will be basically equal to the negative rate of change of the charge density rho, okay, that is typically represented in coulombs per meter cube, right. So, you can say that divergence of J should ideally be minus dou rho dot T, okay. So, this is what is happening. So, as I told that the electric currents basically obey the continuity equation, which is this, and from Gauss law we have known that divergence of D basically gives you that rho. D is the electric flux, right. So, in other words, it looks like that this is basically this one. So, to make it come to 0, you have to basically add something to it. So, you can intuitively see that curl of H is not only J, there is basically something more than J, okay. So, that is what Maxwell found out, and he knew that a time varying magnetic field gave rise to a solenoidal electric field, which is the Faraday's law. So, why not a time varying D field would give rise to a solenoidal H field, right. So, with that, because the universe loves symmetry, Maxwell introduced a new term called displacement current density, that is called JD, which is basically dou D dot T, okay. Now, what is this term? So, if you look what Maxwell has done, Maxwell has basically added this new term, right, in the Ampere's law, and now this equation becomes Ampere-Maxwell's equation, right. So, this is a complete one. It tells you that a flowing electric current gives you magnetic field that basically circles the current. So, that was coming from the Ampere's law, and then Maxwell basically added this new term, and it says that a time changing electric flux density also gives rise to a magnetic field that circles the D field, and that is basically the Maxwell's contribution. And the second part, this part is introduced for electrodynamics, right, and that is how you can write curl of H is not only J, it is basically J plus JD. What is JD? JD is dou D dot T, and okay, so you can basically get this particular equation. So, what is happening? Once again, now if you take the divergence on both sides, you will have divergence of curl of H, that is 0. Divergence of J is basically giving you minus dou rho dot T, and then divergence of D will give you rho. So, this term will give you plus dou rho dot T, this minus dou rho dot T and this plus dou rho dot T, that will give you 0, and that is how this equation is also satisfied. So, the fourth Maxwell's equation is basically telling you that the magnetic field can be generated in two methods, namely with electric current as well as changing electric field. So, finally, here we can summarize the Maxwell's equation in terms of the static and the dynamic fields, where E and H fields are basically independent in the case of electrostatics or magnetostatics, but they are coupled in the case of time varying or electrodynamics. Okay. So, the equations here on the left shows the equations for electrostatics and electromagnetics, but as soon as they are dynamic in the electrodynamic, these new terms in blue, they are basically added up. So, these are the Maxwell's equation in the integral form, and these are the Maxwell's equation in the differential form. Now, we know basically how we can go from one form to the other. So, the Maxwell's equation in integral form gives you a much more clearer picture and an understanding about the entire scenario, from which we can derive these differential forms which are easy to compute, okay, using some theorem like Stokes theorem or divergence theorem. With that, now as we know how to determine the electric and the magnetic fields in electrodynamics, we want to now determine how these fields will propagate through a region, and this can be described by the electromagnetic wave equation, which is basically a second order partial derivative that describes the propagation of an EM wave or electromagnetic wave through a medium or in vacuum. So, here you can see how the wave is propagating, and you have electric field vector which is oscillating along the y direction, you have the magnetic field vector oscillating along the z direction, and the field is propagating along x. Okay. So, the homogeneous form of the equation, you can also think it of like this: you have electric current which is having a circulating magnetic field, and then you have a electric field between the loops and so on. So, this is how they are coupled and they are propagating forward. So, the homogeneous form of the equation can be written either in terms of electric or magnetic field. So, del square E r t is 1 by v square dou E r t by dot E square. So, this is how typically the wave equation looks like. So, it can be written for both electric field as well as magnetic field. Okay. So, our goal here is to determine how the wave equation can be derived from the Maxwell's equation. So, you can see the Maxwell's equation here. So, let me throw out a vector identity. Okay. So, to start, let me throw out a vector identity which is basically a mathematical manipulation that is true for all vector fields, and here we will assume that we are in a source free region. So, no charges are there and no current is flowing. So, we will start with this equation, say curl of E equals minus dou B dot T. So, B is mu h, so you can write it like that, and then you take curl on the both sides. So, you can see it is curl of E, which is nothing but minus mu dot dot T curl of h. Okay. So, you can use this particular vector identity that curl of h equals grad of the divergence of h minus Laplacian of h or del square h. So, this is basically the gradient of the divergence, and this is Laplacian. Now, for the magnetic field, the divergence is 0. So, this equation basically boils down to curl of h will be minus del square h, and because of the symmetry, you can also write the same equation for electric field, and that is also fine because we are talking about source free region or region where no current is flowing. So, you can also write that curl of E is minus del square E. Okay. So, if we go to this equation, that curl of E equals minus mu dot dot T curl of h. So, what we have seen that the left side can be written as minus del square E. What about the right side? The right side is basically having curl of h. So, curl of h can be represented from the fourth Maxwell's equation, that is J plus dot D dot T, right. So, these equations become like this. So, you have minus del square E, which is basically mu dot dot T J plus dot D dot T, right. Clear? Now, because there is no current, it is a source free region, this term also becomes 0. So, what you have, the left side remains as it is, right side only becomes minus mu. Okay. So, where is the minus coming from? So, you have from the curl equation, curl of H, you can write it as minus del square E equals minus mu dot E j plus dot D dot E. Now, because it is a source free region, this j term becomes 0. So, you have minus del square E equals minus mu, D can be written as epsilon E. So, you have epsilon outside. So, you will have this one, okay, which is nothing but the second derivative, partial derivative of E with respect to t. Okay. So, this is how you get. So, del square E is basically mu epsilon dot square E dot E square. Fine. So, this is the vector wave equation. So, now it actually is basically 3 equation, because you can think of Ex, Ey and Ez, okay, with the 3 components of the electric field. Now, we will also see how this wave equation can be used to obtain the speed of the electromagnetic waves. So, the connection between electromagnetic waves and wave optics is now more evident. You can see that the wave equation, which is basically the basis of wave optics, is basically embedded within the structure of the electromagnetic theory, and the speed of the electromagnetic wave is related to the electromagnetic constants epsilon and mu. So, if you want to obtain the speed of electromagnetic wave, you got to compare this equation, okay, that you have just obtained, del square E equals, here it was, if you see from the previous slide, here it was mu epsilon. Okay. So, mu is basically mu naught mu r. So, relative permeability and vacuum permeability. Mu r is 1, okay, in vacuum, and in for any other material or in most of the material. So, you take mu naught only. Epsilon can be written as epsilon naught, that is the vacuum permittivity and the relative permittivity, and then you have this term. If you compare it with the wave equation, you will see that this term is basically 1 by v square. So, you can say v square is basically 1 by mu naught epsilon naught 1 by epsilon r. So, this first ratio is basically c square, that is the speed of the light in vacuum. So, c square divided by epsilon r, right. So, you have these values, these are the constants people use, mu naught, epsilon naught, and from that you can obtain what is c naught, that comes out to be very close to 3 into 10 to the power 8 meter per second. So, this is how you can obtain the speed of light or speed of any electromagnetic wave in any medium, which is basically having this epsilon r. So, this is v square c naught square. So, if you want to find what is v equals c divided by square root of epsilon r. Now, if this material is lossless, then square root of epsilon r will be simply the refractive index of that material. Okay. So, with that we will conclude this lecture. So, we will go into the electromagnetic properties of materials in more details in the next lecture. If you have got any query regarding this lecture, you can always drop an email to me at this particular email address mentioning the lecture number and the course title on the subject. Thank you.